Hi everyone, this video is about the charge balance which we need to write when using the systematic treatment of equilibrium, which just as a reminder is related to the fourth goal of our course. When we use the systematic treatment, we're going to write down all of the chemical reactions. So maybe, one reaction that we'll always write is the dissociation of water. That's something that will always be part of our system. So we'll write down all of our reactions and their expressions for K. So in this case, for water, it would be a Kw, but we may also have to write down Ka, Kb, or a Ksp. So we'll write down our reactions, we'll write down their expressions for K, plus two more equations, and they are the charge balance and the mass balance. This video, again, will focus on the charge balance. The charge balance says that all solutions are electrically neutral, and I really like the example or the way that Harris says it. He says that when we're working in the lab, we know that solutions must be electrically neutral, because if this solution had an excess positive charge and this solution had an excess negative charge, wouldn't beakers be sliding across the tops of lab benches because they were attracted to each other? Clearly, that doesn't happen. All solutions are electrically neutral. So let's see if we can do this example. Let's write a charge balance for an aqueous solution containing all of these ions. Now, one subtle point to remember about these charge balances, notice here that it says aqueous solution. That means that H plus and OH are always going to be present in our charge balances, even though they may not be listed here. H and OH will always be present. So when we write a charge balance, we're going to put our positives on one side of an equal sign and our negatives on the other. So let's write the positives. I might start with this H plus because I don't want to forget it. Positives on one side, that's H plus, and our sodium, and our negatives, oh, and I forgot a calcium. Positives on one side, negatives on the other, that would be OH from water and chloride. Now, this is almost correct. There's one subtle point that we're missing. I want to ask you to consider sodium and calcium. Imagine that the concentration of this sodium ion were 1 molar, so I might say that I had 1 mole of sodium per every liter of solution. Again, that's just the concentration. But if I think about it, for every 1 mole of sodium, don't I have 1 mole of positive charge? So what we see here again is the concentration of sodium, and what we have here is a coefficient of 1, and that's what we do in fact have in our charge balance. But things will be different for calcium, wouldn't they? If I had the same concentration of calcium, 1 molar, that's 1 mole of calcium for every liter of solution, couldn't I say that for 1 mole of calcium, I have 2 moles of positive charge? So again, this would be our calcium concentration, and look what we have here, a coefficient of 2, which is missing from our charge balance, and therefore we have to add it. Now our charge balance is correct. So that's an important thing to remember, that in a charge balance, the charge of an ion becomes the coefficient. The charge of an ion becomes the coefficient. And that coefficient is always positive. So even if we had, say, sulfate on the right-hand side here with our negatives, it has a -2 charge, its coefficient would be a +2. In a charge balance, the charge of an ion becomes its coefficient. Let's try to do another example. So here they want us to write a charge balance for arsenic acid, and it was kind of nice that they showed us how arsenic acid ionizes as a triprotic weak acid. So again, positives on one side, negatives on the other, and let's remember the charge of an ion becomes its coefficient. So the only positives I'm seeing in this solution are H+, and again, even though it may not be apparent from these equilibria, you're in water, so a negative is always going to be OH. Remember, H and OH are always present. So now our other species containing arsenic, we would have dihydrogen arsenate, and then we would have hydrogen arsenate, but the charge becomes the coefficient, and that coefficient is always positive. And then finally, arsenate, with the charge becoming the coefficient, and with that coefficient always being positive. So this would be the charge balance for a solution of arsenic acid. Those are all the examples I have. Thanks for listening, and I hope you try some on your own.